I'm glad that it rubs you the right way there. Okay. As always, you can choose to write down everything, some of, or none. I encourage you to pick the middle one. Let's begin. What is friction? Well said, Nick. A force that resists motion. It involves objects that are in contact with each other. Does there have to be contact with each other? No. It says it involves objects that are in contact with each other. Like if you're, is there friction when you take like sandpaper to a 2x4?
Yeah. Yes.
Yes, of course, right? The sandpaper is in contact with the wood. What about when you throw a baseball through the air? Is there friction?
Yes.
Air is air friction, right? It actually, it has to push aside and rubs up against the air molecules, right? So there must be contact.
What? Is there friction when you throw a baseball?
When you throw a baseball, yeah.
And I said not when Kieran throws it.
Oh, got to the second base. So what causes friction? Now, there's actually some controversy. They're not entirely sure. I'm going to give you the basics, but they're still speculative. They haven't confirmed a lot of findings. They're still investigating friction, which is hard to believe here in 2015, right? So an object deforms a surface and vice versa. Some people believe that when you put a book on a table, like so, that when you zoom in on that little area right there, that what's happening is the table actually gets sort of deformed, and the book the box sort of sits inside that little hole. On a molecular level, right? It's pushing down those little table molecules slightly. And so that plowing force is required to move the object over these deformations, sort of like uphill all the time. That's one theory. Irregularities interlock and offer resistance to movement. When I say irregularities, I mean like just sort of little bumps, right? Like if you zoom in, what you've really got is that kind of thing, right? Things are not perfectly smooth. And the little sort of peaks and valleys sort of lock in together and they break off like sandpaper, right? Like after you sand, it's smoother. How come? Because you broke it off material, creating sawdust. That kind of thing, right? When your shoes wear down, right? If you look at the bottom of your shoes, they're sort of worn out, right? Unless they're brand new. How come? Friction wears off the rubber off the bottom of your shoes. Wears off the wax off the floor. Okay? Well, let's not get into that just quite yet. We're getting there. Now, there is some idea that you can actually make things too smooth, and they're actually, the atoms are so close together that there is that attraction that's why it's referred to. I'm going to look out and see if anyone's still right. The other thing you can do, it looks like Kiana's doing, is she's finding what I'm finding in that notes there, just highlighting. Is that what you're doing? Yeah, that's a good idea too. I'll post this later too, so you'll have it if you want. Okay, now you should know the difference between starting friction and sliding friction. So starting friction is the maximum frictional force between stationary objects. When you try to get something moving, it has that inertia, it's hard to move. But starting friction is also greater than sliding friction. Sliding friction is the frictional force between objects that are sliding with respect to each other. So like, pushing a chair across the floor, that kind of thing. Most things that we move tend to roll. Rolling friction is actually a situation or a subset of starting friction, because the tire, as it rolls, that piece of tire that's in contact with the road or whatever, the floor, is at rest, and it's just as the tire rolls, it's the next piece. It's right here. Okay? Basically, anything that is moving, assume it's sliding, even if it's rolling friction is way too hard to figure out at this point in the game, so just assume that we're sliding. Up to now, I've given you the friction force. I've just said friction is like minus 2 newtons, right? I've just given it to you. Okay, we're going to take a step back and I'm going to make that a little bit more realistic for you today, i.e. harder. Pause for cheer and celebration. There's none coming.
Next slide.
Okay. So some properties of friction, some qualities, some characteristics. Friction always acts parallel to the surfaces that are in contact, and always in the direction opposite to the motion of the object or to the net force tending to produce such motion. That's a lot of words to describe what's going on here. Okay? It's always parallel to the surface. And I think you probably intuitively know this, right? Like I'm pushing this way, applied force, friction force, right? Parallel to the surface. If the surface gets rotated, friction rotates as well, right? If you push really hard, friction will oppose that. What if you don't push very hard at all? Just lightly. Push on the fan counter just sort of like this. Friction still opposes it, right? It only pushes as hard as it needs to. Like it's not gonna, if friction, maximum friction here is say 50, and I push with 20, does it go flying backwards because 50 is pushing this way? No. That'd be cool. But it'd make things a little bit awkward. Every time you pushed on something, right, you'd have to push hard enough to,
Or come flying back.
or come flying back at you.
That'd be a lot of unnecessary.
There'd be a lot of broken noses. Friction depends on the nature of the materials in contact and how smooth they are. And generally, the smoother they are, the less friction there is, to a point. What kind of objects have a lot of friction, or produce a lot of friction? Yeah, rough things, right?
Or heavier maybe?
Weight does get into it, mass. Well, yeah, we're going to get there, right? If you've ever fallen like on the track outside, you know there's a lot of friction, right? Falling on the track out there?
Yep.
In Nipawa, yeah, maybe it would have smoothed down. Okay, so those are 2 properties there. I think that they exist. If I'm not mistaken, these properties are right there on the right-hand side, right? Page 1. So if you're highlighting or whatever, you can do that. No need to write them all down. Sliding friction is less than or equal to starting friction, so they could be equal, but generally starting friction is bigger. And people know that, right? When you push, there's a lot of friction to start, and then once you get it going, it's pretty good. Friction is practically independent of the area of contact. Now, there is some controversy here. People think about like skinny bike tires compared to like the big wide tires in a drag car, and they say they have those big wide tires because of friction. More friction, you can go faster. Well, that's not exactly true.
Yeah, because there's less weight on it.
It's all about pressure and it's about the heat, because if they had the narrow tires, there'd be too much heat, and then they would degrade really fast, right? So, generally, area is not a component of friction, contrary to popular opinion.
Little bike tires on the truck that they spend probably more than
Yeah, I'm not.
So this is what Kieran's talking about here. Starting or sliding friction is directly proportional to the force pressing the 2 surfaces together. So I'm going to draw the classic picture here, the box on the table, right? Weight force, mass times gravity. If the mass is bigger, gravity remains the same. If the mass is bigger, what happens to the amount of force down? It's more, right? Which means that the normal force is increased and the friction is bigger, right? And that makes sense, right? Like, if I'm trying to push this table here, I'm trying to push this table across the floor, right? And Dylan decides it's not going to happen. He jumps up and sits on the table. increases the mass of the table considerably. Is there more friction? Yeah. You do, no, not bad, but he's larger than the size of the mass of the table. He's increased the mass of the table. So that's where it comes into play here. Okay? It doesn't it increases the friction. I gotta try something else here right away. If you haven't written anything down yet, this should be your first. Or at the very least, find that on the notes and circle it, highlight it, put a box around it. This is the big idea. The coefficient of sliding friction.
Right here.
It's right there. The coefficient of sliding friction is the ratio of the force of sliding friction to the normal force.
What's that little symbol?
That little symbol there is the Greek letter mu. Mu is how it's written in English. It's the Greek letter M. It's probably the first, well, no, you've seen Greek letters before. What other Greek letters have you seen? You've seen theta, yeah. You've seen pi. No, it's sliding friction. It's not mass. Yeah. Now, I often wonder, what do the kids in grade 11 physics in Greece? Holy. What letters do they use in their formulas? Like, do they use mu for and if it's Greek letter M, what do they use for mass? Like, do they have F equals MA? Do they write mu alpha? And so when we went to Greece, I said, I'm going to ask some kids on the street. And my wife wouldn't let me. She thought it was creepy.
Wait, you did it?
No, she wouldn't let me, but I really want to know. Just walking around a kid. So, you take physics. What do you do? I want to know. I tried Googling it. Like in geometry, do they use theta? Well, they must, right? I don't know. It was the summertime.
Trying to find a Greek math curriculum.
Yeah, I'll have to do that. I don't sleep very well at night.
Go to school.
So, mu is equal to the friction force over the normal force. Friction force is that number Ff that I've been giving you. Fn is usually equal to the weight force, which is usually equal to mass times gravity, right?
Okay. So what is the MU?
The mu is a measure of, it's a number that tells you how much friction there is between those two surfaces. Like if I took a rubber tire and rubbed it on an asphalt road, the mu value is about, I think it's about 0.4.
But wouldn't that just be the friction force then?
It's not quite. It's a measure of how much friction there's going to be depending on the weight. Okay? Well, when I do the samples, it'll make a little bit more sense for you.
And the FN was
The Fn is the normal force. It's how much weight is pushing down, right? And so when you increase this,
so if like you had like a 1 kilogram calculator and you put it on the table, that would be your FN.
yeah, times 9.8. 9.8 newtons. Yeah. It's going to make some sense when you see the examples, right? Okay. This number here is a constant. Now, constant is a relative term. Pi is a constant, 3.14, it's always that. Gravity is a constant, 9.8, it's always that. But mu is a special kind of constant because it changes. Yeah, it changes depending on what surfaces you're talking about. When you do wood on wood, it's about 0.2, 0.25. Okay? Things that are rougher, higher. Rubber on concrete is going to be about 0.5 or 0.6. Teflon on ice is really, really low, like 0.01. Okay? Okay. Do you have this example question written down there? You do on the second hand of everything, right? Okay, so just to save some time, I've given that to you. Okay? We're going to do 2 examples, and then we're going to give you a chance to work. We're going to do the third one on Monday. Okay, so go ahead and draw a box on the floor. Draw it better than me. Really cool. We have a box. Okay, Lane. Lane, let's do a couple samples, and then you'll have a chance to have a little visit with Greg, because I know you missed him from yesterday. A box with a mass of 174 kilograms pulled along a floor with a constant velocity. Please underline that, and I would encourage you to do that when you're doing questions, because that is very important.
What is that?
Why is it that important? Well, let's draw our free body diagram. Weight force, normal force.
Oh, check mark.
We're applying some force here, so it's FA, and because it's a constant velocity, Nick, force is equal, right you are.
Solid forces are equal.
Unit force.
Are these two are equal, not necessarily the same as those, but the up and down is equal, and the left and right are equal, right? So constant velocity is important because it tells you that the applied force and the friction force are the same.
Yeah.
Okay?
Yeah.
Okay. The only other number I have is the coefficient of friction, the mu, between the box and the floor is 0.34. What horizontal force is exerted in pulling the box? What am I solving for here? Which one? What symbol? What letter? FA. What horizontal force? I'm trying to find the horizontal force.
Cole, just don't say anything.
That's okay, Cole. The weight force, Cole, is mass times gravity, right? Okay, so if FA is equal to FF, if I find FF, that's going to tell me FA, right?
Yeah.
How can I find FF? I'm going to use this new formula. Do I know FN?
Yeah.
I'm going to. I know mu, that's how I get FF, right?
Yeah.
Okay, so first step, generally, it's never a bad idea to start any solution with the weight force is mass times gravity. Even if you don't need it, well, you almost always need it. So let's start with that. So 175 times 9.8, again, notice how I write the formula, line up the equal signs, show my work, even though I can do this in my head.
So are we just going to keep 9.8 as positive now? Or what?
You're going to be one of those, are you, Lane?
No, I'm just asking.
I know.
You never put it, so should I just not put it in?
Go ahead, put it. Jimmy crack corn, man.
Yeah.
No, it's probably a good idea to put it. Well, let me finish the problem, and then we'll come back to your question, okay?
Okay.
Because I will answer it. I'm not avoiding the question.
Negative 1750.
Negative 1715?
Yeah. 1.5.
Okay. So, if the weight force is negative 1714, you guys, did I teach you about the 3 dots?
Yeah.
Therefore,
Yeah.
that means that the normal force is, means therefore. That means that the normal force is up 1715. So in answer to Lane's question, technically he's right. Yes, it should be negative. That should be negative. And yeah, it's kind of one of those things that we like,
I'll just be.
So then you go 17, 15.
hold on. Okay, so now mu is
Yeah.
FF over FN. .34. From the question. Now, how do you solve this?
2.34.
Yep, multiply both sides. And I'm going to write it out so that you can all see what's going on, even though I know what's going on here. Showing my work.
Bill, what is it equal?
58. Oh no, okay. 583.1.
583.1, right.
What newtons?
Newtons.
So
That means, again, we're going to get to use the 3 dots. Therefore, because the FA and the FF are equal, therefore the applied force is 583.1.
You need to put that?
Yeah, you do, because it actually says what is the horizontal force, right? Like, if you just leave it like this, you're actually saying that's the friction force.
Okay.
Okay? Now, I want to ask you a question here, but I'm going to wait till everyone's done, because I need to make sure that everyone's listening to this. What are the units for the force ones? No, units. Newtons. What's the unit for mu? Like, you know what I mean by units, right? Like meters per second, grams per cubic. What's the unit for mu? 0.34 what? Well, the answer is 0.34 nothings. Because what is mu? It's a ratio of friction force over normal force, and friction force is measured in newtons, and normal force is measured in newtons. And can you cancel units? There is no units for mu. You know, in 20-some years of teaching this, there's always one in every class, and when I introduce mu, that's what they do. I just expect it now. Yeah. And I can usually predict, like, weeks ahead who it's going to be. And once again, I was right! Okay, as always, let's start with a picture here. Even if I'm not giving you a mark, it helps. If you make mistakes along the way and I look at the picture and I see, okay, they get something here, then I might be able to give you a mark here, right? So you should have it like this, where the applied force is significantly greater than the friction force. Okay, Cole?
Yeah.
Stop wrestling, please.
Yeah.
Dylan, stop allowing him to wrestle with you. Well, stop. Weight force. Mass times gravity. 100 times 9.8. Negative. Minus 980 newtons. Therefore, normal force is plus 980 newtons. Mu is FF over Fn. Again, I point out formulas, lining up the equal signs, left to right, spacing in between. 0.2. Friction force.
So he's only got 96. He's accelerating.
So what is this, 96? 196. Yeah, that sounds familiar. Okay, so in the previous example, that was the applied force, that was that. But in this case here, there is a net force. Exactly. F net is the applied force plus the friction force. So in this case, it's 200. Now, should this FF be negative 196?
No. Isn't it 100?
Yeah.
It should be, because it's opposite that 200. Are you going to get negative out of this mathematically? No, you have to put it in. You have to assign it a direction of minus 196.
Where'd you get this?
Almost there.
And yes, I know it's not the same on the paper. I apologize for that. I fixed
Listening
it.
skills. Yeah, listeners on attention.
Which means now my net force is a mere 4 newtons.
Your F.
And now
F equals
F net equals MA, 4 equals
Oh, that's what.
100A, and you get a very tiny acceleration of 0.04 meters per second squared. Is that hard?
Yeah.
Well, it's a step up.
You made it seem easy.
I know. And again, I point out that if I fired this out to you on day one, you would have all run for the door and run down the guidance and dropped it. But now I've just added a little bit more to what you already know,
Now it's too late to drop.
adding a few more pounds to the barbell, if you will.
Already maxed out though.
Already maxed out? No, there's always room for more.
Already maxed.
There's always room. Okay, I'm going to stop talking because no doubt you're tired of listening to me.
Oh.
You can feel free to agree with that if you want. There are some problems here on the backside here. Again, I point out there are answers, there's solutions there. On Monday, Peter, you got all day to do that. On Monday, I will do example number 3.
Oh, yeah.
Okay? I'm going to check to make sure that my question matches yours before Monday. And then I'll give you some more time to work on Monday. We're just going to do one sample question. Those people, bad people, I'm going to give you the next sheet. In fact, let me even see here.
So what did he do here? 4 divided by...
4 divided by 100, right?